During a recent discussion, SpaceX is implementing solutions to fix issues with the Raptor, 2 engines for the Starship version, 2 in preparation for Flight 9. Elon Musk has announced a new problem with the Raptor. Elon Musk inadvertently revealed that SpaceX's Raptor 3 engines are currently facing a technical challenge. Although the Raptor 3 represents a significant leap in performance over earlier versions, ongoing development has exposed specific issues that need addressing. While Musk did not go into full detail, his comments suggest that the problems are complex enough to require further design refinements and testing. This disclosure highlights both the rapid pace of innovation at SpaceX and the inherent difficulties in pushing rocket engine technology to new extremes. Elon Musk inadvertently revealed an issue currently facing the engines, specifically the Raptor 3 variant that SpaceX is developing and preparing for flight. Many improvements still to come. But recently, Elon Musk revealed that even this advanced engine has its flaws, describing some parts as ugly and unreliable. How is that possible for such a cutting-edge piece of technology? Elon Musk recently, albeit unintentionally, shed light on an ongoing issue with the Raptor 3 engines, the latest iteration of SpaceX's high-performance Methalox engines. Although Raptor 3 promises substantial improvements in thrust, efficiency, and manufacturability, current tests have revealed persistent challenges. These may involve combustion stability, thermal management, or material stresses at the extreme pressures Raptor 3 operates under. Musk's remarks underscore the complexity of advancing engine technology, even for a company accustomed to rapid innovation cycles. The ugly, unreliable, and heavy-bolted flange between the thrust chamber and hot gas manifold will become a welded joint. As we know, all of Starship's test flights so far have used Raptor 2 engines. So, given the timing and content of Musk's comments, it's clear that he's referring to Raptor 3. Raptor 3 is the latest and most advanced evolution of SpaceX's Raptor engine, engineered to ultimately succeed the Raptor 2. Like its predecessors, it utilizes a full-flow staged combustion cycle, one of the most efficient and complex engine cycles ever developed. This cycle is named for the way it handles propellant flow. But before diving deeper into this issue, we have to remember that SpaceX has never publicly released any test video for Raptor 3. This makes any predictions we can make about Raptor 3 seem rather vague. In fact, there have been some photos of Raptor 3 tests, but whether those tests were successful or if there were any issues has never been disclosed by the company. This performance was made possible by SpaceX's groundbreaking changes to the Raptor 3's design. And now, with additional comments from Elon Musk, it's becoming more certain that Raptor 3 is facing some technical challenges that require significant refinement before it can be put into operation. While Raptor 3 features a significantly simplified design compared to Raptor 2, Elon Musk's remarks suggest there are still some notable limitations. One key area of concern is the connection between the thrust chamber and the hot gas manifold. Currently, this connection uses a bolted flange, which Musk describes as ugly, unreliable, and heavy. In a rocket engine, the thrust chamber is where the combustion of propellants occurs, producing high-temperature, high-pressure gases that generate thrust. The hot gas manifold, often part of the engine's plumbing system, distributes these gases or propellants to other components, such as injectors or turbines in stage combustion or gas generator cycle engines. The interface between these parts operates under extremely harsh conditions, temperatures over 3,000 degrees Celsius, pressures ranging from dozens to hundreds of atmospheres, and intense vibrations. This joint must be extremely robust, leak-proof, and able to handle thermal expansion. Mismatches. Newer Raptor versions, especially the Raptor 3, are designed with fewer bolted joints and more reinforced welded joints. Older engines used bolts like screws in furniture, easy to remove and replace. Raptor 3, their use as welds, like using superglue instead, stronger and lighter but much harder to undo. Great for performance but not ideal if you need to make repairs. A bolted flange is a mechanical connection where two components are fastened together with bolts, often using a gasket to ensure a tight seal. While flanges allow for easy disassembly and maintenance, they come with a number of drawbacks. ones even Elon Musk finds unacceptable. Firstly, the flange adds unnecessary weight to the Raptor engine. It requires additional materials for the flange itself, bolts, and sometimes reinforcement structures. In rocket design, every kilogram matters because mass directly affects payload capacity and fuel efficiency. Secondly, flange joints are prone to leakage, especially under the cyclical thermal and pressure stress is experienced in rocket operations. Gaskets can degrade, bolts can loosen, and misalignment during assembly can damage the seal. Additionally, this type of connection demands precise machining of the mating surfaces, bolt holes, and gaskets, raising manufacturing complexity and cost. Assembly also takes time and introduces the risk of human error. Aesthetically, bolted flanges appear clunky and visually unappealing. To completely address this issue, Elon Musk has decided to replace the bolted flange in Raptor 3 with a welded joint. And rightly so. Welding is a star in the field of rocket manufacturing. A welded joint eliminates excess materials, potentially saving several kilograms depending on the engine's size. It forms a continuous material bond, making it far less prone to leaks or mechanical failure. Modern welding techniques like laser welding or electron beam welding can produce extremely strong defect-free joints even in high performance alloys like Inconel or stainless steel, both commonly used in rocket engines. Reliability is especially critical for reusable rockets, where engines must withstand multiple firings without maintenance. A welded joint can reduce the need for inspection or repairs at that interface. Beyond performance, a welded connection offers a cleaner, more integrated look and structure, reducing stress concentrations and improving gas flow dynamics inside the engine. In high-performance systems, smooth transitions between components help minimize turbulence and pressure loss, potentially boosting overall engine efficiency. However, in order to fully transition to welding, SpaceX clearly must also confront technical challenges, even though welding itself is nothing new to the company. While welded joints offer obvious advantages, implementing them is no simple task. Rocket engines operate in extremely harsh environments, and the transition to welding requires careful engineering to ensure success. The first issue is material compatibility. The thrust chamber and hot gas manifold may be made from different materials or alloys to optimize performance, e.g. copper alloys for the chamber's inner lining due to high thermal conductivity and stainless steel or Inconel for the manifold. Welding dissimilar metals can be challenging as it risks creating brittle intermetallic compounds or weak joints. Advanced welding techniques such as friction, stir welding or laser welding may be necessary to achieve a strong bond. Another drawback of welding is reduced maintainability. Bolted flanges allow the thrust chamber and manifold to be separated for inspection, repair, or replacement. A welded joint removes this flexibility, making maintenance more difficult. However, along with the amazing developments and achievements, there are always technical trade-offs behind the scenes. The integration of cooling circuits into the engine components requires sophisticated design and manufacturing processes. Each part must now serve multiple functions: structural, propulsive, and thermal management, which increases the complexity of both the design and production processes. This also leads to maintenance and repair challenges. The new design with welded parts instead of flanges makes maintenance and replacement of components more difficult, requiring cutting of welds. This is a trade-off between overall reliability and ease of maintenance. Achieving ever higher thrust and combustion chamber pressures requires engine hardware that can withstand these extreme conditions. Elon Musk has commented that the Raptor operates close to its physical limits. What SpaceX has accomplished in the past and continues to achieve today is proof of that. SpaceX succeeded with the technology behind this next-generation engine, known as the full-flow stage combustion cycle, which for decades had been considered nearly impossible by traditional aerospace companies. Although both the Soviet Union and the United States conducted extensive research on this technology. No engine using this complex combustion cycle had ever been put into operation. Yet only 6 years after Elon Musk announced that SpaceX was designing the Raptor engine, they had completed the first flight-ready model. The full-flow stage combustion cycle is often regarded as the holy grail of rocketry, as it promises to extract the maximum amount of energy from its liquid propellants. In a field where every ounce matters, gaining even a few more % of thrust is worth pursuing. Especially if, like SpaceX, you plan to use these full-flow engines on the largest operational booster in spacecraft in the world. Many of the most famous rockets ever flown have used engines based on what's known as the gas generator cycle, including the Saturn V, Soyuz Delta IV, and even the Falcon 9. In fact, aside from the space shuttle, one could argue that nearly every major milestone in the history of spaceflight has been accomplished with gas generator engines. This is a technology dating back to the V2 rocket and one of the key breakthroughs that made liquid-fueled rocketry viable. A gas generator produces gas to spin turbines, which in turn drive the propellant pumps. In some engines, the gas generator operates independently from the main engine and has its own fuel supply. For example, the V2 rocket's turbines were driven by steam created from a chemical reaction between hydrogen peroxide and warm potassium permanganate. The drawback of this approach is that the secondary fuel system for the gas generator adds weight and complexity, exactly what you want to avoid in a rocket engine. A more modern method used in engines like the Falcon 9's Merlin is to power the turbines by burning a relatively small amount of the same propellant and oxidizer used in the main engine. In this case, the gas generator is usually called a pre-burner, but if the pre-burner uses the same fuel and oxidizer mixture as the main engine and at the same ratio, it's essentially just a smaller rocket. Engines are becoming not only more powerful, but also more cost-effective and built to fly many times over. This progress is a clear sign that humanity's drive to explore beyond the boundaries of our planet is stronger than ever, and it's not slowing down anytime soon. And that's about it for today's episode. Thank you so much for tuning in, and that's all for today's update. If you enjoyed watching and found it useful, please make sure to subscribe to my channel and hit the like button. And if you want to support our channel and if you want to be up to date, you can become an exclusive member, so click on our perks through the link in the description below. Thanks to watching and see you next time.